Okay, so it's all connected, it's all good. All right, well, Rodney, do you want to?
Hey guys, this is the same class from last week, right?
Yep.
Okay, so fellas. So, you guys know part of what my job is the internship developer for the department. So currently last week, I developed an internship with a company, they're based out of Folsom. They're called Untitled Technologies. So what they do, they're a technology company that offers technical support for large and small companies. And right now they are looking for a student from ARC for a paid internship. And this has a possibility they're looking to hire someone for junior systems administrator. So they are currently looking to interview our students here at American River College. And my job is to go out and find a student that they're looking for. They're looking for someone to hire right now, pretty much. I told them that we are in our finals week, dead week, and then finals week. So, and then the position is paid. We're looking for someone to work up to 30 hours a week. And I said that could possibly work right now because school is out in a few weeks. So if you guys are interested in the position, please come by my office. I'll talk to you. There's just some housekeeping things that we need to take care of. And then I will set up, we'll be doing interviews next week since school's out the week after next. Everybody got one? So the things on the bottom is what they are really looking for. They're looking for someone who have server and routing knowledge, excellent customer service skills. The reason why they want someone with excellent customer service skills because when you pick up that phone or you're out on site, when someone's computer's down, they're what? Upset. So they want to they don't want to lose business. They want to keep their business what they have right now. And then looking for someone to ability to grasp new concepts and develop new skills. A driver's license and a vehicle. You guys probably won't be going off site right now, but if you get hired on as a junior systems administrator, there's a chance that you will be going off site. And then that's about it. So it's paid internship. How much? I'm not sure because it's going to be dependent on education / knowledge. So they told me that. So it's going to be not sure how much. So it will be paid up to 30 hours a week. Next semester when you guys go back to school, they're going to work around your schedule and then they're going to see what's best. And hopefully out of the candidates they have here, they're going to hire that person. What they want to do is keep that person on and hire that person for a junior systems administrator. That's what they're looking for. You guys have any questions? No? Quiet bunch, huh?
Well, you can talk about, a little bit about how internship can be helpful to students,
Do you guys know about internships? You guys are familiar with internships? One thing that I hear a lot from students is this. Companies want you to have experience. What's a good way to get experience? An internship. Internship is the ability to work and learn while you're in college, get some valuable work experience, and once you graduate, the first thing the company's going to look at what type of education you have, what type of certificate you have, what type of training you have, which is great, fantastic. But then they're going to say, what type of work experience do you have? Well, I have a year here. I have 6 months here. Okay, so now you're more employable. Now you can come in and hit the ground running. So that's one thing that questions that I receive quite often. People say they want work experience, and how do I get work experience? And it's an internship. So in this right here, I'm on a roll lately. I've been getting a lot of paid internships. Paid internships does not come very often. Most internships are just for work experience, just for a chance to come in, and then it takes a lot to develop an internship. It takes a corporation and a company to say, we're going to have a staff member who's here going to train and help this student. It takes not a lot from a student, so internships work around your schedule. So if you have class every Monday, Wednesday, Friday, and you can work Tuesday and Thursday, the employer knows that, and the employer is going to make your work schedule Tuesday and Thursday. If you can work 10 to 2 on Monday and Friday, they work around your schedule. They're probably the only time the employer is going to work around your schedule because they know you're in school and they're trying to help you out. So, and then with the internship, there is a class associated with it. It's called Work Experience 498. And I did hear someone talking about SAC say, don't get scared. It's not a class that you go do homework. What's your homework in your internship class? Is what? Huh? It's your job. Yeah, that's your homework. So that's your class, is actually working. So your midterm is your midterm evaluation with your employer. You'll sit down with your employer and then they'll say, how do we do things? How am I working? And then they'll go, they'll talk about that. So it's not a class, you won't be doing papers, you won't be doing assignments. Your assignment is working right now. So this is one great thing about my position here is we have a work experience program for the whole district. So, but my position is, the reason why I really enjoy my position is every internship that I develop here stays here. So, for example, if this internship was for the district, every other student from the whole district is going to be competing for this internship. But my position here at ARC, every internship that I develop stays right here at ARC. So instead of competing with 2,000 students, you only have 20, whoever applies for the internship. So that's a good thing about my position here, and that's why I see fruits from my labor. So, and I really enjoy giving you guys opportunities. So this right here is an outstanding opportunity to get some work experience and get paid for it and get transferable units too. The work experience 498 class is transferable. So if you're going to Sac State or CSU, you actually get credit and paid to get an internship. So this is a good one. It's paid. It's you guys' major. It's a good company. I've already talked to the owner. I went there. It's a good place to work, and they're offering a paid internship. So hopefully, you guys will come over. You guys will talk to me, and then you guys will get an interview. All right? Any questions? Yes.
Should we email you our resume?
Yes. So I will need a resume and unofficial transcripts. Those are the housekeeping things. In order to receive the internship or be eligible for internship, we need to make sure you are a student and in good standing. So that's for the unofficial transcript. It's very simple. And then active resume. It doesn't matter. One thing about an internship is the employer doesn't care about what type of work you've done now. They know you're a student and they know you're trying to get some work experience. Whatever you might have. I don't care if it's McDonald's, Safeway, or nothing at all. That's what we need to send you a resume. And then each employer is going to want to see it. That's how it works. That resume, yeah, sure. Send it to them. So, right. So I'll need a resume and unofficial transcripts. And then that's it. And then we'll talk about some other things over in the office. And then, so my job is I vet all students. So when a student shows up for the employer and gets an interview, that student is everything what they're looking for. So it works out. So it's a good relationship for everybody. All right. You guys know where my office is at? Next door. Okay. Any other questions? Yeah. What's up, man?
What time you're available?
I'm there today. You guys out of class at what time?
10:30 more or less.
10:30. All right. Cool. So I'll see you at 10:30. Probably, man. Come on. Any other questions? So this company right here, they're very anxious. They're looking to get someone. They understand school is almost out, but they're just excited about getting a student in. So they're like, okay, let's get in fast. I'm like, hey, look, man, just started. I just told her the last week, so it's going to take some time. So, but they're a real good company, real good owner, and they're just anxious to get a student in there.
How many positions are available?
One. So, because they're a small company, and they're looking to see a lot of internships they'll say we got 4 or 5 internships, but they're looking to hire. So they want to invest in an intern to roll that intern over into a junior systems administrator. So that's what they're looking for. So they're going to train, invest their time, because that's what they really want, and that's what he said. He said we really wanted to roll this intern over into a junior systems administrator. We'll work around the work schedule. We just want someone that we can invest in, pay them, because we understand, and that's another thing too. This company understands that people have to work, go to school, do whatever. So they're going to pay the student, give them training, and if everything works out, hopefully it does, they want to roll that student over into a junior system administrator, and then still work around their schedule too. So it's a pretty good situation right now. Any more questions? Yes, no? All right, perfect.
All right.
Thanks, Ed. All right.
Thank you, Rodney. All right. So I kind of drew, on my tablet, as Rodney was talking. For those of you who kind of have plans, yeah.
Have you guys know about our design hub over there?
Some people do.
Okay, you guys, I can be in there all day talking about that. You guys need to start looking at the design hub and the opportunities they have over there too. So,
I'll talk about it.
Oh, all right, cool. They have a lot of opportunities over there. Some are paid, some are not paid. And the design hub is on campus, so you guys don't even have to leave campus. So you can get internships that way too, and all types of things. And you're looking for it, and it's a really cool thing going on right here on campus that you guys should definitely be a part of. All right, so yeah, but I can talk to you about that if you guys come over there too. All right?
Okay. All right, cool. Thanks, Rodney. So anyway, I was just drawing this little picture here. I think that kind of internship program is really, really helpful for people who are already planning to transfer to Sac State, because Sac State is local, and that company is in Folsom. I know it's not exactly local, but it will still be local, regional enough, so that someone who's going to Sac State, can be continuing, with that internship if it turns into a part-time or full-time junior position. So that's kind of a nice, setup, because you're continuing with a 4-year university, your bachelor's degree program, and at the same time you have a part-time or full-time job, at a local at a local company to pay for your fees and whatnot. So I think that's actually not a bad gig. But the point is, there's I think Rodney mentioned this several times already. Is the company had basically has plans to transition the student internship position into a full-time / part-time junior position kind of job, and those internships are very, very difficult to come by. A lot of internships are really just using students to do some of the lower end work, do some of the chores and stuff like that, so they can save their employee time, so they don't have to do all the low-level stuff. But from the description here, if you got a copy, they are really planning to it's basically checking out potential future employees. This is how this company works. So it's kind of a difficult to come by type of opportunity. Even though the internship position is desktop technician, which doesn't sound very sexy, right? I mean, it doesn't sound very I don't want to be doing desktop technician for 20 years. But when you look at what the company does, there are definitely opportunities to transition to other types of jobs. So I would at least check it out. Okay, look up the company, find out what they do. Are there any opportunities to transition from a support position to something that is kind of more interesting? It looks like they have to do diagnostics also. And I would say computer security is probably on their list too, even though it's not shown on this piece of paper. So anyway, just something for you guys to consider. The Design Hub is on campus. As Rodney said, it's on campus. It is on the other side, so-called the other side. It's right across from not the nurseries. They call it the child care center thing. So it's right across from there. So the Design Hub, we have a few people in this class, who are already kind of somewhat participating in the Design Hub activity. So you can ask, those students for more information. So they do offer internship positions. Some are paid, some are unpaid. You'll be working on actual programming projects that will turn out something that is useful to either people on campus or some people that are off campus. But they are real projects. They're not, just toy projects. And they do count as real internship, which means we do have a record of what you do, how you perform. So later on, when you need a reference, this can serve as your first few references, because that's the difficult part. If you want to go out for a job, they ask for experience. Every single job wants experience. So how do you get started? It's a chicken and egg problem. So the solution to that problem is internship. So anyway, that's basically what Rodney is trying to come across and convey. Yep.
Is there somewhere we can access Design Hub online or something?
To access
Is there online information?
the Design Hub. The Design Hub doesn't have a whole lot of stuff that is published, but on the other hand, I do have almost full access to that document system, because I'm one of the faculty members on the Design Hub thing. So if I go to shared with me, I can show you what kind of stuff they are working on right now. So let me look up one of the folders. Design Hub logo. No, that's just the logo.
It's on the bottom.
Design Hub access implementation workbook year 1. Okay, let's check this out. Okay, so this is the grant implementation plan. So that's kind of really boring stuff. Presentation. Huh. If I go even further, I can. Sorry? Spring 17 projects. So these are the projects from last semester. So they got quite a few things. They got 3D scanner adapter for Simple 6, print board, ANCO scan, aerial mapping. Many of these are not computer related, but this semester, fall 2017, they got many projects that are computer programming related. One thing that's actually for their own infrastructure is they use Google Documents and Google Spreadsheet to keep track of hours of the so-called intern students, right? And they have a QR code scanner, so that when someone gets into the Design Hub, they use a phone and they just take a picture of the QR code, and that logs them in, and then when they log out, it's the same thing. But in order to do the calculation, Google Sheets doesn't do all the calculations, and somebody wrote scripts to basically do all the calculations, do all the summation, do all the reporting and whatnot. And I know they're still looking for people to continue to expand that program so that they can automate a lot of the stuff that otherwise would have to be done by hand. They're also, aren't you guys doing the database
I don't
thing?
work there.
Somebody is working on the database, right? Darren.
Oh, for the club, yeah. Darren is in charge of that. So
Yeah, the database for support.
the crisis support, yeah.
Crisis support stuff. So I think he's supposed to come to me because he has a MySQL variable issue that he could not resolve.
Oh,
So
I haven't heard.
I'll see him in the club meeting. Maybe not today because I have Damon's evaluation meeting at exactly the same time today. So anyway, there are all kinds of projects. So if you have not stopped by the Design Hub, before, just go ahead and stop by. Tomorrow, let's see, today is Tuesday. So on Thursday, at about noontime, they are open at that time. So noontime on Thursday, just right after this class, right after the lab, walk over to the Design Hub. They are over at Tech Ed room 311. So if you look up Tech Ed 311, okay, I'm just trying to see if there's a map here.
It's right across from 306, which is the physics class.
Yeah, it's also right. It's right across that. It's also right to the north of the child care center. So yeah, just listen for kids screaming, and it's in that direction. Is it kind of quiet in there, or do you guys actually hear the kids when the door is open?
Oh, I've never heard that. Kids.
Oh, okay. Okay.
I don't know when the kids are actually there, because most of the time I go by, it's just empty.
I know they do have kids sometimes, you know. So anyway, are there any questions about the Design Hub? No questions? How many people are kind of planning or looking into getting an internship before you graduate from here? Few. Okay, very good. I think it's just a good experience. And some of you already have jobs. I know that you're already, you know, having a job outside of the campus. So you may not need an internship as much. Okay. All right, so getting back to the homework assignment. Are there any questions about the homework assignment? So let me go back to this class and then we'll take a look. Yeah, go ahead.
Oh yeah, just about the multiplexer that connects the data port.
Okay,
the flags out.
All right, so let's.
There's data bit conflict. And I was just wondering if like my solution is like on the right track, because I kind of use like a splitter to split the 8 bits to 8 bits, and then the merger only taking the 5 bits, left out the last 3. Or if you're supposed to pad it.
You have to pad it regardless, because the data bus is 8-bit wide, the register is only 5-bit wide.
Right.
So you have to pad. I would pad the most significant 3 bits to be all zeros.
Okay.
Yep. Okay, so let me show you what I have here. Okay, so this is what we talked about last time, you know, for this particular class. And let me zoom in. Okay, so this is the portion that we talked about last time, is the flags out of the ALU has to go into a multiplexer, and then the data bus has to go to the other end of the multiplexer, and then the output of the multiplexer will go to the D port of the flags register, so that this way you can use the multiplexer to choose which source should I use to update the flags register. Because right now, you know, the existing architecture can only update the flags register from the ALU, but you want to change that. But that also means that this wire here, the red wire, where it goes to, which is FC, might need modifications as well. The equation for FC may need to be changed, because you need to update that equation so that it's not only updating the flags register when you perform an ALU operation, like add, subtract, and, or that sort of thing, but you also have this one extra instruction now that is also supposed to update the flags register. Okay, so the difficulty of this particular assignment is not really so much the opcode that you're supposed to implement for the assignment itself, but it is to maintain backward compatibility with all of the existing instructions. That part is actually more difficult. So that you basically have to look at all the existing instructions, especially the ones that would use the data bus, and make sure that your new hardware that you add to this whole thing does not interfere with the existing instructions. And that part is going to be a little bit more involved, because you might need to change this equation or change this negation flag, but you're free to change the processor as much as you need to in order to get it done. So are there any questions? Yeah. Did I answer your question?
Yeah, so you pretty much had the 5 data bit input with zeros to match the.
Yeah.
So we can just change where the red line is and leave FC as it is?
The red line?
Yeah, where you have your red line, we can make a modification there and leave FC as it is?
You will need to make the instruction work and also maintain backward compatibility.
Yeah.
That's the objective.
Yeah.
But you can make any changes that you want. Yeah. So the bottom line is we don't want to make any changes to any microcode slices of existing instructions, nor the width of the ROM. So as long as that objective is, you know, achieved, as well as the new instruction is implemented, it's all good. So there's a lot of degrees of freedom, you know, to get this done. But it's also complex in the sense that you want to make sure that the new instruction does not interfere with existing instructions, or the new architecture interferes with old instructions. So any other questions about the homework assignment? Nope. Okay. So I'll leave this page up here for now, and then the next thing we'll do, or next thing I'm going to do, is to take a look at exam questions. So we'll go to exam questions from previous semesters and kind of check those out. At least we'll get to know what kind of questions will be asked in the final exam for this class. So, so we'll check out this one. At this point, it may not be shared yet. I'm not 100% sure whether it's already shared or not. So I'll also check that, make sure that this is already shared. So I go to the share folder. Let's see, where would that go? Final answers. Previous practice. I'll just make a new one. I'm gonna make a new folder, old final exams. And then I'll just copy this document over there. So this one is in fact spring 2017, because from the date of the exam, this is when it is done. So we'll make a copy of this document to the new folder, which you already have access to because it's inside the share folder. Everything under the share folder you already have access to. Okay, I got one too many levels up. Go to the share folder, go to old final exam. Okay, select, and we'll call this one, the proper name, which is 17 spring final exam. There we go. So you should be able to see it now, in the share folder. You don't have to check, I'm pretty sure it is the case. So the final exam is kind of like all the other two exams. It is open book and open notes. You can bring anything that is either printed or handwritten prior to the test that you think will help you. No electronics other than a scientific calculator. Okay. I don't think you'll need a calculator, but if you want to bring one, that's fine. So in the previous year, all questions have equal weight. I think I will maintain that property in this final exam. So they will all have equal weight, which makes it easier for you guys to evaluate and go like, okay, which one should I start with? Because if they all have equal weight, you just find the easiest one to start with. But if they're not equal weight, then it's harder, because now you have to say, okay, this one is really easy, but it only has like 50% of the points of the other ones. Should I start with this one or not? But this way is easy. Okay. So I also make a really short list here of what is considered correct code. The stack has to remain balanced with items cleaned up immediately after use, particularly for subroutine calls. The correct flags used for signed versus unsigned numbers, even if the range of numbers being tested may not trigger incorrect behavior. So that means, if I specifically say that an integer is signed, then any comparison should utilize the L flag instead of the C flag, to determine whether a number is less than the other number or not. Registers assumed saved by callee remain unchanged when the callee returns. Okay, registers assumed saved by callee remain unchanged when the callee returns. I have no idea what I meant by that. I think I've completely forgotten that. I think what it meant is registers cannot be saved by the. You have to assume registers are not saved. The callee, whatever subroutine you're calling, can change all of the registers, including the flags register. To reverse engineer code, the C version should not contain any go to, continue, or break statements. In other words, the C code should be entirely structured. Okay. No corruption of memory locations assuming incoming parameters are correct. None of the compiler or assembler should produce errors. We don't have a compiler, but so that only applies to the assembler. Okay. Yep, go ahead.
From that one, maintaining the C code structure, do you want us to do that with the assembly code? Like making sure the labels don't have like conditional jumps before continuing on?
Okay, you're talking about this point, right?
Yeah.
Yeah, so what I do not want to see would be the use of goto, which is, which you can actually use, syntactically you can use goto, but I do not want to see gotos in your solutions. I do not want to use continue. I don't want to use the use of continue or the use of break.
Oh, I see. So when we actually
Reverse the engineer. Yeah. Yep. All right. So we'll check out the questions. So question number 1. I think we might have seen this before. Okay, I'm not sure. Write the assembly code in mnemonics for the toy processor for the following code. You may use labels, and there is no need to assemble the code to opcodes. Because if I did not specify this, there was one student from the semester before this one who hand assembled everything into actual hexadecimal opcodes. So I go like, no, that's way more than what I needed. Okay, I just need the mnemonics. Okay. All variables are global in this question. Assume the variables have some values when this code executes. The ASCII code of digit 0 is 48, and so on. Okay, well, first of all, do you see the use of any global variables? Nope, there are no global variables. What about x? What is x? X is a parameter, so it's not a global variable. All right. So I already tell you the ASCII code of 0 is 48, and the ASCII code of 9 is 57. So that means I'm telling you the integer values of this thing as well as the integer value of that thing. Your code must use all the caller-callee convention as discussed in class, as well as how the stack should be used. Okay? Okay, so do you guys want to do this one or not? Do you think this is like, it's too easy? I think this one is simpler than some of the questions in your exam too. All right, so how do we do this?
It's returning an int, so there is that special call to save the register.
Okay. So I'll do it on the side using my tablet. Okay, so we'll do it on the side here and go all the way to the bottom. Okay, so the first thing is we know that it needs an entry point, which is digit. So that's a label for the entry point. It's always helpful to kind of track what is on the stack at any particular time. And my convention, is to use square brackets to indicate what the stack point is pointing to, and then use round parentheses for the other, extra variable registers. So in this case, at this point, when I'm at the entry point of the entire subroutine, I know there are two things on the stack that relates to this function call. The first thing that, so the convention that I use is whatever is on the left-hand side is what? Is high? Okay. I think it's low. Whatever is on the left-hand side is low. Whatever is on the right-hand side is high. So in this case, the return address is here, and then the parameter x is here. The square brackets means the stack pointer is pointing to the return address. Okay, so what we need to do is to compare the parameter x with the ASCII code of 0, which is 48, and the ASCII code of 9, which is 57, and make sure it is in range. If they are in range, I return a value of 1. If not, we return a value of 0. Okay, so we have to get to x. So the first thing, the usual trick is to use a CPR, CD, so that this way, we have both of those registers pointing to the return address at this point. And then we do an increment C. So once we have that, the stack pointer will still be pointing to the return address, but register C will now be pointing to X. Okay, but we're not quite done yet, because register C, oh, you cannot see the entire thing. Because register C is really the address of parameter X on the stack. It is not the value. We are not comparing the address of X to the ASCII code of 0. We are comparing the value of parameter X to the ASCII code of 0. So that means we need to dereference it once before we can do the compare. I do not have any use of this address any further, so I can clobber C at this point, which means I can do LDCC. Okay? So the effect of LDCC, I'm really hoping that everybody understands what it does now. Okay, it is just dereferencing register C, grab the content at that location in RAM, and then put it back into register C. Okay. So after this, C really is just parameter X. So now we can do some comparison. So to do the comparison, I would need an LDI instruction. I can choose register A or B. It doesn't really matter which one. I'll load register B with 48. Okay. So the idea is I want to. In this case, it is easier to check when it is out of range, so I can get out. Okay, so I want to basically do a comparison so that I can just use a JLI. Now, why JLI and not JCI? Because it is signed. It is actually signed. Okay, so the characters are actually signed. Okay, so we want to use a JCI after the comparison to go to the else label. So now the question is, how should I formulate my compare instruction? Should I compare the value of X, which is in register C at this point? Should I use CB or BC in this comparison? Okay.
BC probably.
CB. Okay, because we want parameter X to be less than 48 to get to the else, because in that case it is out of range. Okay, because in the C code, when it's out of range, we get to the return 0 code. But there are two reasons for it to be out of range. One is X is less than the ASCII code of 0, and the other one is X is greater than the value of the ASCII code of 9. Okay. Okay, so that's the first comparison. Yep.
Were you intending to write JLI or JCI?
Oh, JLI. Yep, you're right. I said it should be JLI, and then I wrote JCI. Okay, so it's JLI to else. Okay, so next we're going to do LDI. We can reuse register B and load it with 57 this time. So this time, how should I do the compare? We should reverse it, right? Because we want to say, let me think. We want it to be greater. We want X to be greater than 57 to branch to else. Okay. So the reverse way to say that is we want the ASCII code of 9 to be less than X in order to branch to else. Okay, so BC is correct. So we point BC here, another JLI here to the same label else, which is going to be defined later. Yep.
Don't we want it to be less than or equal?
We want it to be less than or equal to get to the then branch.
Yeah. Okay, but if it's less than 57, we want to go into the if, don't we? Because at that point we know it's greater than 48, but less than 57.
But when you combine these two, it means if 57 is less than parameter X, we go to else, which is correct. Because it is out of range in that case.
Oh, right. Okay, yeah.
Yeah, because we kind of flipped the logic. We're looking for excuses not to go to the then branch, basically. Okay, so now at this point, this is our actual then branch, which doesn't really have a whole lot to do. Just a single LDI A with 1 will do the trick. Okay, but it is also important to do JMPI to end if, because otherwise it will fall through to the else label. And then I'm just going to continue up here. So now we have the else label here, which is a LDI A with 0. Or if you want to, you can do a subtract AA to clear the content of A. Either one works. So now we have an and if, and at this point we can do the usual return code, which is LDB with D, because we are retrieving the return address from the stack, and then we increment the stack pointer, and then we do a jump B, to utilize the return address that we just retrieved. So that's the one solution to this problem. I mean, there potentially are other ways to do it, but this is one way to do it. So are there any questions about question 1? There will definitely questions like that, okay? Like in question number 1, where I give you the C code and you translate that into assembly code.
Can we keep it this simple?
Then there'll be more. There'll be at least one that will check whether you know how to call subroutine in assembly, and this one doesn't check that. So there will be one at least that you will be calling other subroutines or the subroutine itself. Yep, go ahead.
Are there going to be more questions since we have the 2-hour testing period?
I think this one only has 5 questions. I can be wrong here. Okay, we'll check. Okay, question number 2 is decompiling. Okay, so we want to decompile the following code into C. There are 2 subroutines. There's main and then there's sub1. Be sure to include as much information about types, that sort of thing. Be sure to use structured code and infer as much type information as possible. And that would include type information of return values, type information of parameters, local variables, and etc. If there are parameters or local variables, you can name those in whatever way that is C syntax correct, and as long as the references are consistent. I think this one we might have done before. Yep.
Question though, do we have to keep track of the flags in situations like this when we need to sub DD to get it to 0?
On the side, yes. Okay, so you need to kind of keep track, but as long as you don't see any conditional branches, the flags are pretty much ignored. So the only time the flags is actually important is when you see a J and then a flag, I, then you need to find out, okay, who set those flags right before the conditional branch instruction. Yeah, so this one, is a little bit longer. So with a problem like this, what you need to do is I think you know how to do it already, because it is also in your current test, or the test exam number 2, is really to look at blocks. Okay, you look for indications that are, okay, this is clearly this kind of operation, this is clearly this kind of operation, and then just step by step reverse the whole thing. Okay, I think we have done this before. Do you guys remember? This is a nested call of the subtraction subroutine. We're using the result of a subtraction as a parameter to another subtract. Yep. Okay, you remember that? Okay, so cool. So we're going to move on to another one, to the next one. If we have time, we can come back and look at this one. Okay, so this one is about the implementation of a new operation. In other words, your exam 2 is already looking into many of the questions that was in the final exam in the previous semester. And I think we might have seen this one already too, because this is the actual solution. That's the actual answer. Let's see, question number 4. This one is recursive. Implement the following code in assembly code. And this one is recursive. I think we have done this one too. Yeah. Yep. So we can probably look into another one. Is that okay? So I'll keep this one up for now. And then what we'll do is we are going to look into an earlier one. So 16 fall. And then we go to the final exam of that one. Open it, and then we make a copy. Alright, make a copy to the shared folder, the old final exam. So go up, and then shared old final exam. And then this one is 16 fall final exam. So we'll get rid of all that stuff. So it should be in that shared folder now. Okay. All right, so this one is even simpler. Okay, this one does not even use parameters. So W, X, and Y are all global variables in this case. So you can see how they are declared here as global variables. They're outside of some function definition. And it's also mentioned here in the question that all variables are global in this particular question. So when something is a global, it means it has a static location and there's a label corresponding to that location, which makes accessing a little bit easier because you don't have to use the stack pointer and figure out where it is on the stack to get to it. So this question is, I would say pretty easy to do. Okay, next question, another decompiling question. Let's do this one. Okay. And I'm just going forward to slide to look at what the return instruction that's in the test in exam 2. And then we have the L flag. The L flag is dirty, so instead of using the L flag, how do we make use of just the other conditional branch instructions to deal with? And then this one is about adding with carry. So how do we add? It's about the 2's complement of 2 bytes, a 16-bit integer. Okay, let's do this one first. Okay, so this question is about the implementation of a 16-bit integer. X underscore low, is the least significant byte. X underscore high is the most significant byte. Okay, so we are dealing with X itself being a 16-bit number. So in terms of a picture, you can kind of imagine that X itself is a 16-bit number, but since the toy processor is an 8-bit processor, you can only process 8 bit at a time. This is bit 0 to bit 7, bit 8 to bit 15. Okay, each chunk is a byte, okay, which the toy processor can handle. X underscore low refers to just the least significant portion. X underscore high refers to the most significant portion. Is that okay so far? So the question is asking, if I need to do the 2's complement of X, how do we do it using the toy processor instruction? Okay, so let's go ahead and take a look at this one, but this time we'll use the instruction set that is available to us this semester. Because in the previous semester, the increment instruction was not available. But this semester, it is available. So the first question is that going to be helpful? Okay, so we want to perform, according to the question here, we want to perform, write the assembly code to compute the arithmetic negation of the value X and store it back to the same 2 bytes. Okay, that's what we want to do. So how do we do it? This is not using the stack, it's not in the subroutine, so all 4 registers are available for you to use. So kind of use that to your advantage. But how do we do an arithmetic negation, which is different from a logical negation? Okay, what is arithmetic negation? Flipping the sign. Flipping the sign, okay? So how do we flip the sign of a value represented as a signed integer? Okay, come on, you guys, hopefully you remember. We are trying to change the value 26 to negative 26, right? So what kind of bitwise operations should we use in order to accomplish that?
You can knot all the bits.
And then?
Either add or subtract one.
Yep. So we're trying to implement 2's complement. Okay. So 2's complement of a particular bit pattern, let's say X here, is 1's complement of X plus 1. The 1's complement is also known as bitwise knot, and then so it's bitwise knot of X plus 1. Okay. All right. But X in this case is a 16-bit number. So let's do the bitwise knot first. Bitwise knot is really easy to do. Which instruction should I use for bitwise knot?
No.
Yep. Very good. Okay, so there's a knot instruction. The knot instruction performs bitwise knot. and it will perform bitwise not. It's one of the very few single operand type of instruction. It only takes one register, so it will do a bitwise not of the value of that register, and then store it back in the same register. Okay, cool. So let's do the bitwise not first. So to do the bitwise not in this case, because x is stored in static location, we can do it in any particular order. Okay, you'll do the bitwise not of the low byte first or the high byte first. It doesn't really matter. So we'll need a LDI, a x underscore low. Okay, so now a points to the low byte of x. So the next thing you need to do is to do an LD instruction. I want to keep a pointing to that location because I'll need that again. So I'm going to use LDBA. Okay, so the comment here is a points to the low byte of x, and then b is the low byte of x. So it is very important to find out or to differentiate a is a pointer and b is the actual value of the byte. So once I have b, okay, I can now perform the not instruction. Okay, it's just not b, so now b is its own bitwise negation, which is the same thing as b is now the bitwise negation of x low, and then we can store it back. So we'll go ahead and say st a b. So we are now storing this back, which means b x underscore low is the bitwise not of x underscore low. Are we doing okay so far with this? And then we can do the same thing with x high. Okay, x underscore high, we'll do the same thing. Okay, LDI a x underscore high, LDB a not b, st a b. So now we have, by the time of these instructions, these 8 instructions, we would have computed and negate the bitwise not of x, stored it back into those same 2 locations. So here comes the tricky part. We're now trying to add 1 to the 16-bit number. But we have the add instruction, we have the increment instruction. Which one should we use? Yep.
I was thinking that you would need a sort of like an if statement.
You need a conditional statement. Why would you need one?
To check for overflow.
Not overflow. Overflow has a very specific meaning when we perform addition. It means the sign of the output does not make any sense. But in this case, it is not going to be sign sensitive. In other words, we know the number is already signed. Okay, so we're not going to check for overflow. What are we checking?
The carry flag.
The carry flag. Okay, so it sounds really kind of odd because we are dealing with a signed number, right? And yet we care about the carry bit. Well, that's because when you perform addition itself is sign blind. It doesn't really care about the blind. It's the same mechanism to perform addition, whether you're adding 1 to a signed number or whether you're adding 1 to an unsigned number. But we are adding 1 to a 16-bit number, but you can only perform addition in 8-bit chunks. So you have to add 1 to the least significant 8-bit first, and then if it has a carry, then you perform another add 1 to the other one. Is that okay? Yep, go ahead.
When you store x high into what a is pointing to, doesn't it overwrite it? Have to decrement it and then store it?
Decrement.
Because like you store x low into what a is pointing to.
Yeah.
The address of a, and then you store x high at the same back into a. So wouldn't it?
Yeah, but I reload a. A is now the pointer pointing to x high.
Oh, okay.
Yeah, so it should be fine. Okay. So what this is telling us is these 8 instructions is really doing the same thing as x equals to the bitwise not of x. Okay, we're done with this part. The next part, okay, I cannot extend the slide because the slide is only this far, only this long. So the next part, okay, let me open another sheet to do this. So the next part is something that looks really simple. I just want to add 1 to x. Okay, x is already negated bitwise. Okay, but x is a 16-bit number. So now we have to break it up into 2 different operations. The least significant byte is easy to handle. So we have a LDI A once again with X low, and then we do a LDBA. Okay, so B is actually the value of the least significant byte. And then here's the question: should we do a increment or should we do a add here? Either one will work, but you just have to be careful. So one more time, let me ask you: should we do a increment B, or should we do a add instruction here?
Which one says the flag?
Okay, we can do either one. Okay, because if you just do an increment, you can check whether B is 0. Okay, after an increment, if B is 0, it means the carry flag would have been a 1 if we had used the add instruction. We can still check for the same thing. So let me go that route first, okay? Because that's kind of the more unusual route. So I'm going to do an increment here. Okay, so increment B, and then put it back into where A points to. Okay, store to where A points to B. Okay, so this would increment X underscore low. Okay, so this collectively is X underscore low plus plus, or plus plus that. It doesn't really matter whether it's pre-increment or post-increment. Okay. So now we have to move on to X underscore high. In other words, should I add 1 to X underscore high too? Because this thing yields a carry. That is the question. But as you remember, the increment instruction does not change the flag register, which is part of the whole point. I don't want the increment instruction to change the flag register. So how do I know whether we add 1 to FF with X underscore low, which will necessitate an adding 1 to the most significant bit? How do we know?
B is 0.
Yep, we check whether B is 0, and B is still here, right? We haven't destroyed B yet. So now we can perform an AND BB, okay, which is just setting the flags. Okay, it's the only flag I really care about is the Z flag. And we go JZI, okay, we JZI to, okay, let's make it really long, add 1 to X high, okay, otherwise we're done. So JMPI to done, and done is just, somewhere, really, when we're all done, we define that label. So now we have this label called add 1 to X underscore high. Okay, yep, go ahead.
Can you explain why you're using AND again?
I can, because AND BB is doing a bitwise AND of B with B itself, which doesn't do anything to B, right? That's okay, but it will change the flags, because the AND operation inside the ALU will still change the Z flag. How do we know that? Well, because tag said so, right? Well, besides that, okay, we can always look up the architecture. So let me go to 1983. Okay, so once you get to the architecture, you go to the ALU itself, show the ALU, and the AND operation is this guy here. So this is the AND gate, multi-bit AND gate that will perform bitwise AND. The output of the AND is going through the multiplexer, and once you get past the multiplexer, what do we do once you get to this point here? Okay, you see the entire thing goes to this particular gate here, which is what determines the Z flag. So what is this gate here? The gate that is pointed to by that little finger icon.
NOR.
It's a NOR, okay? It's a negated OR gate. So when do you get a NOR gate to output a 1? It is the negated OR.
When at least one is a 0.
No.
When both.
Okay, so it's a negated OR, which means if at least one of the input is a 1, it will give you a 0, because it's negated OR. So the only time it's going to give you a 1 is when all the incoming bits are zeros, which is what we are checking, okay? Which is what the Z flag is about, is the Z flag is a 1 if and only if the result of an operation is 0. So that is how we know the AND operation is the same thing as, okay, I need to check whether this thing is 0. And a register with itself would accomplish that. And on top of that, it will also tell you what the sign flag is, which is not useful in this particular case, but it will tell you what the sign flag is as well. Okay, is that okay? So this is why, you know, this picture or the ALU architecture will still be kind of useful, you know, to bring for the final exam. All right, so getting back to our code here. This part is easy because we just need to add 1 to x_high, so we can use pretty much the same code as before, which is LDI A x_high, LDB increment B, STA B, and we are done. Done is here. So together with this slide and also the previous one, we would have the same, we would have the code to do a bitwise, we would have the code to perform a arithmetic negation of a 16-bit integer, which is kind of like the combination of a bitwise NOT of a 16-bit integer followed by a 16-bit increment instruction sequence. Is that okay so far with this code? Yep.
You said with the increment that you didn't want to update the flags. Can you explain again why?
You mean the increment instruction itself?
The increment B up there.
Increment B up here? Yes. Well, it's just that increment instruction itself does not update the flags.
Okay, that's.
Yeah, it's not intentional, you know, but the other way to do it is to use the add instruction, but using the add instruction is really cumbersome because you have to load a 1 into another register, and then you perform the add instruction. So in that case, if you use the add instruction, then over here, I don't need the AND anymore. Instead, I can use a JCI instead of a JCI, because the add instruction would have indicated whether the carry flag was set or not.
Okay, that makes sense.
But they would accomplish the same thing. Any other questions? No? This is good? Okay.
I'm
Yep.
still confused on how you get a 1 for the NOR gates. I mean, not OR gate.
Okay, so
when B is 0, then should I not have?
when B is 0. Okay, so, okay. Are you referring to this slide or referring to the previous one?
That one. So
This one?
you have,
Okay.
we have comparison and B to B.
This is not comparison. It's not CMPBB. CMPBB is guaranteed to have a Z flag set because you're subtracting a value from itself. This is AND, which means it's performing a bitwise AND of every single bit of B with every single bit of B.
If it's a 0, then how will it set the 0 flag?
Okay, so this is the deal. So what we are doing here is we're performing a bitwise AND, and then we have the 7 bits of B, right? Bit 0, B0, B1, all the way to B7, right? And we're performing bitwise AND with the same stuff. All right? So what do you think is B0 and B0? Now, by the way, we don't know whether B0 is a 1 or 0, but what is the result of something and itself? And this time it's a single bit.
Itself.
Itself. How do you know that? Prove it. You use the truth table. So when you look at the truth table, you have x, y, and you have x and y. Okay. Now we are dealing with logical AND, not bitwise AND in this case. So 0, 0, 0, 1, 1, 0, 1, 1. Right? There are 4 possible ways. When you look at x and y, this is 0, 0, 0, 1. So how is this truth table supporting the fact that B0 and B0 is always B0, even though B0 itself can be a 1 or 0? How do we know that? We look at this row, and we look at this row. Because it tells you that 0 and 0 is a 0, 1 and 1 is a 1. So that means it doesn't really matter whether B0 is a 1 or 0. The conjunction of B0 and itself is guaranteed to be the same as its original self. Is that okay? So this is the kind of stuff that I really want you guys to do, at least in your mind. It's not really just to take it for granted. It's like, okay, text said it's going to preserve all the bits. Okay. Yep.
Why are we updating the Z flag?
Okay, so let me finish this first. Okay, is that okay? The bitwise AND would yield exactly the same bit pattern as what we started off with. Okay? So now the question is, what is the Z flag? The Z flag is the NOR of all the output bits of an operation, right? So it is the same thing as B0 plus B1 plus B2 plus, by the way, in this case means disjunction, okay, up to B7. And then we negate the whole thing. Right? So what is the only time that Z is going to be a 1? When B0 all the way to B7 are zeros. So the combination is we perform the bitwise AND first, which will set the Z flag, and then we use a JZI to make use of the Z flag that was set or reset or cleared by the AND instruction. It's a trick to compare to 0 really fast. Yep.
So the only way that we can actually set the carry flag is if everything before was all 1, so it'd be increment 1.
Yep. Which also has the side effect of B has a value of 0. So that's why I have a separate or different way to check for whether the carry flag would have been set or not. Yep.
It's funny because it makes sense now.
Okay, well that's good. As long as it makes sense, right? And we understand the process to make sense out of it. That is the important part. Okay. Any other questions? And this is also the reason why AND register with itself is an instruction that I have not hijacked, because it is actually useful for purposes like this. In many architectures, they just rename this instruction to test, TST, and then with a single operand, because that's what it is for. Okay. Any questions about this code? Okay, no questions. And let's check the test again and see if we are interested in any other instructions or any other questions. What about this one? This one is, we don't want to use the JL instruction. We want to use JO and JMP, that sort of instructions. Okay, so I'm going to rephrase this question based on what the kind of instructions that we have access to. So instead of doing a J, okay, so it's basically asking this question. Okay, let me switch back to here. So instead of a JLI to L1 instruction, if I do not want to use JLI, but I can use any of the other instructions, how do I do this? That's the question. How do I emulate the effect of a JLI instruction using the other instructions? Okay, so I'm going to use the equivalent symbol here. It's going to be long. Okay. So you can use JOI or JSI, okay? Use one or the other. So I'm going to use JSI in this case. So I would use JSI to one, temporary label, L2. You are allowed to define extra labels in this case too. Okay, I would make it go to L2. What does it mean if I get here? The sign flag is a no. If it was a 1, I would have gone to label L2 already. If I continue execution, it would have been a 0. Okay. So if the sign flag is a 0, what do I need in order to go to L1? Remember how the L flag is defined using the sign and the overflow flag? It is the exclusive OR, right? Which also means they just have to be different. If one is a 0, the other one should be a 1. If one is 1, the other one has to be a 0. So at this point, we know the sign flag is a 0 already. So what do I need the overflow flag to be in order for the L flag to be set? To be a 1. Okay, that's easy. So we can do a JOI to the original intended destination, L1. We're done. Cool. Now we're defining L2 here. By the time we get to L2, we know the sign flag is a 1. Which means but I have no choice but to do a JOI here. I have control over where it goes to, but I have no I do not have any other choices of what instructions I can actually use. So this JOI has to go where?
It has to jump over the.
It cannot go to L1, right? Okay, so we'll label the L3. Okay, so what does it mean when I get here? The sign flag will still be a 1, but the overflow flag is a 0. It's a 0, because if it was a 1, I would have gone to label L3 already, right? Yep. Okay, so the overflow flag is a 0 at this point, which means, hey, the L flag is set again. So let's do a jump I, okay, unconditional branch to L1 in this case, because that would have meant the L flag would have been set already in this case. So now we define L3 over here, and we're done. No, L3 has no particular way. There's nothing to say about L3. L3 is really just a continuation of this whole thing. So the single instruction JLI to L1 is equivalent to this entire sequence of instructions. And that is why it is worth it to implement the L flag. Because if we don't have the L flag, we would have to do all of this stuff in place of the JLI instruction. Yep.
Before the L2 label, shouldn't we need JMPI L3 to skip that?
Oh, you're right. Okay, I forgot that. So this is a JMPI to L3, because by the time we get to this location here, we know the sign flag is a 0, but we also know the overflow flag is a 0 as well, which means the L flag has to be off, which means we should continue execution at L3. Correct. Very good. Okay, so you can look at this entire sequence of instructions. We have JSI, JOI, JMPI, JOI, JMPI. It is consisting entirely of branch instructions. Some are conditional, some are unconditional. Okay, and to us it's just like, oh, it's kind of tedious, but okay, that's nothing too bad. But when you look at a pipeline processor, which we have not really talked about in this class, but most processors are pipelined at this point. Okay, which means they would perform the instructions, or the microcode are structured so that for every single clock, it will perform the first step of one instruction, perform the second step of another instruction, the third step of yet another instruction, the fourth step or the final step of another instruction. So this way, you can actually maximize the use of the circuitry inside the processor. But pipelining does not like branch instructions, because when you pipeline and you do have just calculations like add, subtract, and whatnot, it's okay. But when you have branches, pipeline doesn't work because it breaks the pipe. Because you don't know whether it's going to branch this way or the other way. Okay, so that's why that's the reason why instruction sequences like what we have here is extremely bad for modern processors, because pipelining does not work when you have sequential conditional branches like that. And when pipelining doesn't work anymore, then it will take extra cycles to do all of these instructions, and as a result, it will be extra slow to go through these instructions. That is also why the JLI instruction, even though it's not pure in terms of from the risk perspective, it is practical. It is extremely practical to have the JLI instruction in place of this chunk of branches. So from the practical standpoint, it makes sense. Okay, even though we can say, yeah, but we don't really need a JLI instruction. Well, that is true, but if you don't have the JLI instruction, your processor will be a lot less efficient when it comes to making decisions. Is something less than something, branch, it would be much less efficient in that case. Is that okay? All right. So we are running out of time in the lecture. I will be over at the lab for those of you who will want to get your homework assignment done and you have questions to ask. Other than that, on Thursday, which is our last lecture, we'll just be going through more exam questions, and I was trying to come up with some additional exam questions just for this semester, because the pace that we went through stuff is different for this semester. So we'll go ahead and make additional test questions or practice questions for this final exam.